NV Fitton, Northern Virginia Community College, the second part of our exposition of key functions. These are for powers and roots. The earlier ones were for functions that were made up of lines. Okay, so first among these is one that is familiar to most students. There we go. This is, approximately f of x equals x squared, and I guess we could just call this a quadratic function. Now there are many quadratic functions. Other parabolas than this are also quadratic functions. This and so on. In any case, anytime we have y equal to ax squared plus bx plus c with a not equal to 0, that's a quadratic function. You might be seeing here the root of the word 4. Well, I guess that's because a square has 4 sides. I'm not really sure. In any case, the domain is all reals. The range is not all of the reals because there are no negative numbers in this basic function. It goes from 0 to, well, 0 on up. I'm missing my parenthesis there because I'm off the edge of the screen. Of course, other parabolas have other ranges. All of the parabolas have the same domain, which is all reals, because x squared is defined for every real number. Okay. The square has a corresponding square root function. And this looks kind of like at least one branch of the parabola turned on its side. There. So let's pick out a couple of points on this. Okay, so when I make my table to talk about what points are on here, I'm going to choose my x values strategically rather than just taking 0, 1, 2, and so forth. I'm not taking 2 because the square root of 2, that's not a whole number, so I don't like it as much as I like the others. Okay, and the equation here, naturally, is f of x is equal to the square root of x. Domain, not all reals, because the square root is not defined for negative numbers. However, it is defined for 0. This is a fact overlooked by many people. They think the domain is just positive numbers. No, 0 is also included in the domain because 0 times 0 is 0, so the square root of 0 is 0. The range is the same as the domain. All non-negative numbers. Okay. There. Now, the x squared function is a type of power function. Power function means y is equal x to some integer, positive integer power, like x squared, x to the third, x to the fourth, and so on. X to the third, or x to the x squared, x to the fourth, x to the sixth, all the even powers of x actually look very much the same. Here in the Desmos calculator, which is online, we see y equal to x squared, looks like a parabola, and I have highlighted the points 1, 1, 0, 0, and negative 1, 1. And now I'm going to add to this y is equal to x to the fourth. And look at that. They share these 3 points that I named, but x to the fourth grows a lot faster than x squared, which we're seeing in red. And this is called the unit square between 0, 0, and 1, 1. In this space, x to the fourth is actually less than x squared. If you think about it, 1/2 squared is less than 1/2. It's 1/4. And 1/2 cubed, to the fourth, is 1/16, much less than that. 1/4 as much as that. So, the moral here is that, in the first place, all of the even powers of the power function have substantially the same shape, but as the power gets higher, the curve flattens out toward the sides of the unit square, and x to the 10th power beyond x equals 1 grows much faster than x squared does. We're not going to use x to the 10th in our course, but still I thought you would like to know. Okay, let's erase these power functions. I'm going to leave the important dots up there. And let's look at y equals the square root of x. Notice that it also shares the points 0, 0, and 1, 1 with x squared. And as a matter of fact, if we put the identity function in there, y equals x, we'll see that it goes right through these, and that x squared and the square root of x are, at least on the part of the domain where square root of x is defined, they are reflections of each other over that black line. Cool. Well, I got to talking about this because I was thinking of power functions, and the next one that we have is called the cubic function. And part of it looks a lot like x squared, and part of it does not. It looks sort of like x squared turned around. You might notice that what we have here is odd symmetry. Remember, we talked about spinning a graph around its own axis. If we turned this thing upside down, it would look the same as it does now. The function equation here is y is equal to x to the 3rd power, and the domain is all reals, as it is for all power functions. The range, now we're back to all reals, because when you take, for example, let's let this be negative 1, well, negative 1 cubed, unlike negative 1 squared, is a negative number. Looking back at Desmos again, I'll now add to it the function y is equal to x cubed, and we can see that it shares these 2 points, and it grows faster than x squared, but between 0 and 1 it's a little bit less than x squared. Okay, now let's take the cube root. Okay, now this looks a lot like the graph for x cubed, but it looks like it sort of turned on its side. If I want to start naming values that are members of the function of the cubed root, well, I'm going to pick ones that actually have integer cube root values. So 1 is its own cube root. The cube root of 8 is 2. I'd have to go all the way out to 27 to find another integer cube root. Our real purpose here is to be sure that we understand and recall later the shape of this. So there's the cube root of x, domain, all reals, range, all reals. And let's go back to Desmos to look at that. Okay, now I'm going to erase x squared, and y is equal to x. I don't know how to say cube root in this program, so I'm going to use the exponential form. Cube root of x. Isn't that a nice picture? So again, we have symmetry, a reflective symmetry over the line y equals x, the identity function. And when we talk about inverse functions in section 1.8, we will understand why that is. Okay, so try to look at these separately and understand that they have the same shape, and that's no accident. Now, looking just at x cubed for a moment, let's take another power function that has an odd exponent. For example, x to the 5th power. And now x to the 7th. I'm going to skip 9 because they're getting kind of hard to see. Again, we see that all of the power functions for odd powers have fundamentally the same shape. But our favorite, to be sure, is x to the 3rd power. That one. Okay, well, that's it for the root and power functions.